Okay, now we're back to more abstract stuff. We're going to talk about upper bounds for the absolute values of contour integrals. Now, we're not going to need those estimations right away, but because estimation is a somewhat new skill for us to acquire, and we've already seen with the epsilon delta proofs, then it can be rather messy to deal with inequalities. We're going to talk about it a little bit here so that your mind has some more time to get acquainted with this new approach. Okay, so basically, just like I said, one of the biggest adjustments when we're going from calculus to the more theoretical courses is that precise computation is often not possible. Because of that, computation is often replaced by estimation, and basically the idea is if we can't find the precise value, maybe we can at least find good lower and upper bounds, or even a limit as a certain parameter approaches infinity or some other limit, and that limit might ultimately actually be the actual value. So estimation, therefore, then, because of upper and lower bounds as well as distances to limits, requires that we work with inequalities. And we've seen how that goes when we dealt with the epsilon delta definition of the limit. But because it takes some time getting used to, we want to take some time out and talk about how to estimate absolute value of contour integrals right here. And well, aside from practicing the estimation, we're also laying groundwork for some later computations in which we will need the limits of contour integrals as the size of the contour goes to infinity. Okay, now let's take a look at a continuous complex valued functions on an function on an interval AB. And we're going to estimate the absolute value of the integral from a to b of w of t dt, and that's just smaller or equal than the integral from a to b of the absolute value of w of t dt. Sometimes this is also called the triangular inequality for integrals, and the proof will show why that is the case. And that is because the integral from a to b w of t dt is the limit as n goes to infinity of a Riemann sum of w of tk times delta tk, as we know these things to be defined from regular calculus. The fact that w now has a real and a complex part really doesn't add that much. It adds another coordinate, that's it. And that's less than or equal by the regular triangular inequality. It's less than or equal than the limit of the sum of the absolute values w tk times delta tk. And of course, this part right here is a Riemann sum for the absolute value of t, so this is the integral from a to b w of t absolute value dt as we take the limit. And that's already it. This will be our main tool as things get really, really complicated. I don't think they'll get that complicated in this course. Often this tool becomes a little bit too blunt, but I think, and I've just gone through preparing the slides for the later part of the course there, I think this is about the only tool we will need. And so now the question is, how do we familiarize ourselves with it? Well, let's take a look at the following. If we've got a contour of length L and f piecewise continuous on the contour and m so that the value of f is bounded by m for all z on the contour, well, then the integral of f, the absolute value of the integral of f, is bounded by m times L, and the proof is quite quick. The absolute value of the integral f of z dz over c is the integral from a to b f of z of t z prime of t dt in absolute values still. By the triangular inequality for integrals, that's less than or equal than the integral from a to b f of z of t z prime of t dt. And now we know f is bounded by m, so f of z of t is bounded by m, leaving us with the integral from a to b z prime of t absolute value inside the integral. And that's the length of the contour, so this is m times L, and that's the proof of that. Okay, that looks pretty abstract. Let's take a look at some examples. Take the upper half of a circle of radius r around the origin, and let a and b be greater than or equal to 0. And we want to show that the integral over this contour of e to iaz minus e to ibz divided by z squared dz is smaller or equal than 2 pi over r. Well, first of all, we note that with z being x plus iy and y greater or equal than 0, which is the case when we're in the upper half of the circle, we have that e to the ia z absolute value is e to the ia x plus iy quantity. If you work that out, I times a times iy is negative ay, so this is e to the negative ay times e to the iax from here. Well, e to the iax, the absolute value of that is 1. And this thing, because a is greater or equal than 0 and y is greater or equal than 0, is less than or equal than 1. So that thing is less than or equal than 1. And a similar estimate also applies to e to the I bz, because the only thing that changes is the name, right? So that means that the integral over the contour of e to the I az minus e to the I bz divided by z squared dz is smaller than or equal to the integral of e to the I az e to the I b minus e to the I bz over z squared dz as an absolute value, which I should have put the absolute value in here. Let me go back here. Yeah, okay, I went back and fixed that. I can't formally apply the triangular inequality to a contour integral yet. That's something where I was debating on whether I should introduce some additional notation right now and decided against it. So let's look at this one more time. This integral is just the integral of e to the I azt minus e to the I bzt divided by z of t quantity squared times z prime of t dt. And if I pull the absolute value inside like this, I only make it bigger by the triangular inequality. And well, now we know that this stuff here, this is less than or equal than 2, right? Because this guy is at most 1, and this guy is at most 1, and so that means that the difference, even if the signs line up strangely, is at most 2. And we are on a circle of radius r around the origin, which means z of t absolute value will be r, so we get 2 over r squared, and z prime of t absolute value stays with us. And well, then that is, of course, because the 2 over r squared comes out, the integral of z prime of t absolute value dt over the upper half of a circle of radius r is just half the circumference, which is pi times r. So that's 2 pi over r then, which goes to infinity as r goes to infinity, which goes to 0 as r goes to infinity. Now that is something that was not part of the deal here, where we're just supposed to show that this is 2 pi over r, but basically that's interesting to foreshadow what's to come, and that is we will ultimately let the radius of that circle go to infinity. And so if I just allow or tell Windows to not protect me from myself, basically what we're going to do is we're going to integrate over these semicircles and make these circles bigger and bigger. And for functions such as the one we've just seen in the example, even though the contour gets longer and longer, the integral actually goes to 0, and that is something that will be very useful to us later on. Okay, final example. We again want c to be the upper half of a circle of radius r around the origin. We want lowercase c to be greater than 0. And we want to show that the integral over this upper half of the circle c of z to the negative c over 1 plus c over 1 plus z dz is smaller or equal than pi r to the negative c over r minus 1. Again here, in light of what we've just talked about, pi r over r minus 1 will go to 1, and r to the minus c will go to 0 as r goes to infinity. So that's another one of those integrals that ultimately will vanish in some way. But right now, let's just do the estimate. Integral z to the negative c 1 plus z dz absolute value is less than or equal than, well, we just go in, we parameterize everything, we multiply with the derivative of the parameterization, and then we pull the absolute value signs in to use the triangular inequality for integrals. Now we realize we're on the upper half of a circle of radius r, which means z absolute value will just be r, and on the bottom we still just have 1 plus z of t, and the z prime of t also stays with us. But here we're going to use now the reverse triangular inequality, right? If you want to make a fraction bigger, you make the denominator smaller, and the smallest the denominator can get is r minus 1, and so that gives us the estimate that this is less than or equal than the integral r to negative c over r minus 1 z prime of t dt. Then we of course pull the stuff out that only depends on r, and this is the length of the contour, so this ends up being pi r, so we get the result that we did claim. Okay, that was a little fast, but certainly even if I had gone slower, the computations are equally hard. What needs to be done here, even though this is a very short section and a very short presentation, is you want to read the section very carefully, go through these presentations very carefully to see that you understand every step in these estimates, then do a couple of homeworks, do them right, and then we'll move on talking about integral theorems. Until then.